Problem 414 says to calculate the values of delta U, delta H, and delta S for the following process. 1 mole of liquid water at 25 degrees Celsius and 1 atmosphere is converted to 1 mole of steam at 100 degrees Celsius and 1 atmosphere. The molar heat of vaporization of water at 373 Kelvin is 40.79 kilojoules per mole, and the molar heat capacity of water is 75.3 joules per Kelvin per mole. Assume the molar heat capacity to be temperature independent and ideal gas behavior. The trick to solving this problem is to break it into 2 steps. The first step is liquid water at 25 degrees Celsius being heated to liquid water at 100 degrees Celsius. We start with delta H is equal to specific heat capacity times the change in temperature. We plug in the values that the problem gave us, and when we do this, we also plug in 1 mole because the problem gave us the molar heat capacity, and we have 1 mole of water starting out. So we end up with a delta H value of 5.65 times 10 to the third joules. We can then use the expression delta U is equal to delta H minus P delta V. Because this step involves no phase change, delta V is negligible, and we end up with delta U being equal to delta H, so delta U is also 5.65 times 10 to the third joules. To find the change in entropy, we use delta S is equal to the specific heat capacity times the natural log of the final temperature over the initial temperature. Again, when we plug our values in, we have to multiply the molar heat capacity by 1 mole, and we end up with a delta S value of 16.9 joules per Kelvin. The second step is to take a look at liquid water at 100 degrees Celsius being converted to water vapor at 100 degrees Celsius. To find the change in enthalpy for this problem, we need delta H is equal to moles times the molar heat of vaporization. When we plug in our given values, we end up with a delta H of 40.79 kilojoules. Because the water is being converted to a gas, we have to consider the volume when we use our delta U equals delta H minus P delta V equation. However, since the liquid's volume is negligible, we end up with delta U is equal to delta H minus P times the volume of the gas. We can use the ideal gas law to find volume, which is equal to nRT over P, and when we plug this in for the volume of our gas in our delta U expression, the pressures cancel out, and we end up with delta U is equal to delta H minus nRT. When we plug in our values, we end up with a delta U of 37.69 kilojoules. For this part of the problem, our delta S expression is delta H over temperature, So we plug in our values and we end up with a delta S of 109.3 joules per Kelvin. To find the values of delta H, delta U, and delta S for the entire process, we add up the values we got for both steps, and we end up with a change in enthalpy of 46.44 kilojoules, a delta U of 43.34 kilojoules, and a delta S of 126.2 joules per Kelvin. Remember to pay attention to sig figs and units throughout this entire problem.